Covalent bonds. In this video, you are going to learn about covalent bonds, how they are made, and how they form. If you haven't seen it already, first have a look at our video, Structure and Bonding. Only the noble gases exist naturally as single atoms. All the other elements of the periodic table have partially filled valence shells or outer electron shells. Atoms bond by swapping or sharing electrons in their outer shells. When very different atoms react, like metals and nonmetals, they normally swap electrons. This is ionic bonding. But when similar atoms react, like nonmetals combining with other nonmetals, they share electrons. This is covalent bonding. Nonmetals are found on the right-hand side and upper part of the periodic table. Some common nonmetals are carbon, nitrogen, oxygen, and the halides. They have shells of electrons that are normally half or more than half full of electrons. Since they have a strong attraction for a few additional electrons, it is energetically unfavourable for them to lose electrons, so they share electrons by overlapping orbitals. This makes a bonding orbital, or covalent bond, that contains two electrons. If there is space in the outer shell, a non-metal atom can form double or triple bonds, like in oxygen or nitrogen. In the displayed formula of a compound, we represent a covalent bond with a straight line, like this. We can also represent a covalent bond as a dot and cross diagram. These diagrams show only the valence electrons. To learn more about dot and cross diagrams, watch our video on dot and cross diagrams. Covalent bonds are directional, which means they are in a fixed position, like holding hands. This is different from ionic bonds, which are formed with an electrostatic attraction between charged ions. The overlap between orbitals means that the atoms in covalent bonds are very close. These things make covalent bonds strong. There are two kinds of covalent structure: small molecules, like water, and giant compounds, like diamond. Because the electrons in the bonds are evenly shared, bonds are not polarized. There is little attraction between molecules, and forces between molecules are weak. Compounds made from small covalent molecules have low melting and boiling points and are volatile. They also don't conduct electricity. Carbon and silicon tend to form giant covalent compounds. These bond in the same way, but instead of forming small molecules with one or two bonds, they form four, making up huge lattices or chains of many linked up atoms, the basis of the organic chemistry of carbon or the chemistry of rocks. One common example is diamond, which is made of carbon. Each carbon atom forms four covalent bonds because it has four electrons in its outer shell to share and has space for four more. If every carbon atom forms four bonds with four other carbon atoms, and each of these forms four bonds with four other carbon atoms, and each of these forms four bonds, we very quickly end up with a very large structure. These compounds have very high melting and boiling points because you have to break covalent bonds rather than intermolecular forces to make them free enough to act as liquids or gases. The covalent bonds hold them rigidly in place in the giant lattice. Allotropes of nonmetals bond covalently. Allotropes are different structures of the same element. You can learn more about these in our video, Allotropes of Nonmetals. So to finish, here is a challenge for you. Which of these compounds are covalent? Pause the video for a moment whilst you think. Have you considered their physical properties and where the elements come from on the periodic table? Solved it? Okay. The answer is all of these compounds are covalent. Carbon dioxide, carbon monoxide, and methanol are all small molecules. Organic molecules form covalent bonds between hydrogen and carbon. C70 is a fullerene, a carbon molecule shaped like a rugby ball, closely related to the Buckminster fullerene. Silicon dioxide is a giant covalent structure and just like diamond, but has oxygen atoms bridging between 4 coordinate silicon atoms. Hopefully, you now feel confident identifying covalent compounds and recognizing their properties.